We're not looking for an exact answer. Okay, so you know how when you find the area of a circle, it's pi r squared? Well, we don't use pi for real because pi is a non-terminating, non-repeating decimal that goes on. I mean, it goes on forever and ever and ever and ever and ever, and it would be impossible to actually calculate with pi because you'd need infinity amount of time to plug it into the calculator even. So we round it to 3.14. That's an estimation of pi. Okay. So rounding numbers, using graphs. Anytime you're looking at a graph, if you're looking at a pie chart or if you're looking at a line graph, a lot of times the points on the graph are not exact points. You know, the line will fall between two whole numbers. And so you estimate. You say, oh, well, it's kind of close to 3, so maybe it's like 2.8 or something. You know, you get, it's an estimation. And then using mathematical models is where we write an equation based on, say, have you seen scatter plots before in algebra where you've got like a bunch of plots and you sort of draw a line that mimics the pattern?
Yeah.
So we write the equation for this line that mimics the pattern of the dots. It's not an exact representation. It's an estimation, and then we can use this estimation to predict future outcomes.
Yeah.
So these are not for sure. And this happens a lot in math, and more often in applied math than theoretical math. But anytime people are doing stock market analysis, they're making estimations based on mathematical models because it's impossible to completely accurately predict the stock market because it's based on human behavior, and that's unpredictable. If you're looking at marketing, maybe like a new product, you look at the sales history and you predict how well this thing is going to sell in the future, or you know, should you keep making this product or should you switch to a different product line? And
when it gets purchased and sold.
yeah, these are estimations though, because you can't accurately mathematically model these things because they fluctuate. So so like I said, this estimation is very applied, very real world math. So in order to round, we have to understand place value and the names of places, and sometimes people forget this, so I just wanted to go back over it. So I think up to here, you guys are probably okay in these two areas. And this might get a little, maybe funky. And then the decimals might get a little bit confusing. So you have ones, tens, hundreds, thousands, 10,000s, 100,000s, millions, 10 millions, 100 millions, and then you have billions, 10 billions, 100 billions, and it would continue to go like that. After billions, you have trillions, and then quintillions, and then
They started running out of numbers.
There's a lot of names. So the largest number I know is Googleplex, which is a Google raised to the power of Google.
Oh dear God.
And a Google is a one with 100 zeros after it. Right, but anyway, when you go the other direction with the decimals, you follow the same pattern, but you put a THS on the end of it. So we have tenths, hundreds, thousandths, 10,000ths, 100,000ths, and then you have millionths, 10 millionths, 100 millionths, and it would just follow. It's the same pattern but with a TH. The only thing that's missing, there's no such thing as a one. Right? So, I mean, really, that sounds stupid. One. The decimal is kind of where the one would be, if there was a one. And the only time you're ever supposed to say the word and in a number is at the decimal. So people say 5,300,000, but that's actually incorrect. You're supposed to say 5,300,000 and 50 cents or something. The decimal is the only thing that's supposed to be the word and. So
Remember that.
yeah, people do it all the time. I even catch myself sometimes slipping into that. I'll be like, oh, it's $10,500, but
I was
it's,
really bad with it, there's a little bit.
yeah. So, but the technically and is only the decimal. So, any questions on that? Place value stuff at all? I figure most of it's really familiar. Rounding numbers. You want to look at the digit to the right of the digit where the rounding is to occur. And I will go over that with symbols. And then if the digit is 5 or greater, you round up. And if it's 4 or less, you don't change it. So basically, go over that. Oh, and this symbol right here, curvy equals means approximately. So anytime you actually estimate, technically you should never use an equal sign. So when you find the circumference of a circle, pi r squared, and you use pi, pi is a rounded number, so technically you should always use a squiggly equal and not a real equal because it's not an exact, but we don't do that all the time. But that means approximately. Actually, it technically means approximately equal to. Okay, so what I meant with rounding, we're going to round to the nearest million. So I am interested in millions. So the number I need to look at is right here. That's the important guy. This is 5 or more. So I'm going to round up. And then replace everything else with zeros. So the 1 is going to turn into a 2. So I have 6, 7, 5, 2, and then I'm going to do 1, 2, 3, 4, 5, 6 zeros. Okay, rounding to nearest 1,000, I am interested in this number here. So I need to look at that guy right there. And he is 4 or less. So I'm going to round, or I'm going to keep the same. Or some people say round down. What, down? W-N, not U-M, okay. And then replace with zeros. So this is going to be 6, 7, 5, 1, 5, 9, 3, and then 3 zeros. One. This is the same thing. You round to the nearest hundredth. So you look, if I want hundredth, I look at this number. But the difference is, instead of replacing these with zeros, I'm going to get rid of them. Okay, so this is going to be 3.14. And that 592 goes away. The zeros on the end of a decimal don't add anything. They're just hanging out. So we just don't put them there. They don't make a zeros between the decimal and a whole number make a difference, but zeros at the end of a decimal are pointless. Okay, to the nearest 1,000, I'm going to look at this 1 and 5. So this is going to be 3.142, and everything else goes away. But here you go. So you go to the store and you buy bread and detergent and a sandwich and an apple and coffee. Because, you know, whatever. And they tell you that your bill is $18.67, and you start thinking about how much everything individually costs, and you think, is that right? Well, if you estimate to the nearest dollar, $2.59, the 5 will round the 2 up to 3. The 1 will keep the 2 a 2. The 6 rounds that to a 4. 50 cents we're going to round down because the 4 will keep the 0 a 0. And then 7 brings that to a 6. And so I have 10, 15. $15. And almost everything rounded up. So is $18.67 a reasonable amount for your grocery bill? No, it's not. So this is why estimation, to be able to estimate quickly, is a good thing, because you can go, wait, no, that doesn't seem right. And then make them recheck their math or their calculation, or maybe they rang up your sandwich twice or something, you know. which happens, okay?
Okay,
So we'll do 30 times 40, and that's easy, because zeros just get carried down, and then you multiply the whole numbers. Did you guys know that trick? Okay, so he's going to make about $1,200 a week. And there are 52 weeks in a year, which is about 50. So zeros get carried down, and 12 times 5 is 60, so he should make about $60,000 a year. Okay. The sections of the pie are always representative of percentages. So the whole circle is 360 degrees or 100%. I was in the wrong subject for a second. So here's a circle graph that, according to the Census Bureau, there were 220,948,915 Americans that were 20 years and older. And if this circle graph represents that total number of people over 20, they are defining old age by these things. So some people are saying you're old when you no longer function mentally very well. Some people say you're old when your body starts to give out. Some people say you're old when you become a grandparent. Depending on how the family went, though, you might not be that old. Some people say you're old when you retire. Some people say, I don't know. And then some people say a specific age. Like, you're old when you're 70. Okay, and these are the percentages of those people. So we're going to determine a calculation, like an actual calculation that would tell us the exact number of people, and then we're going to do an estimate to find a reasonable estimate. So first we're going to do the calculation. That's an L. And what do we want? We wanted decline in physical ability is 41%. Now, you cannot work with a percent in a percent format in math. You guys know that? You have to make it a decimal first. And then to go from percent to decimal, it's really nice because if you put them in alphabetical order, they're in the same order that you have to move the decimal place. So to go from a decimal percent, you move 2 places to the right, and to go from a percent to a decimal, you move 2 places to the left. So it worked out nicely that they're alphabetical. So I'm going from a percent to a decimal, so I go here, so 0.41. And to do the exact amount, I would do 0.41 times, what was that, 220 million. 948,915 would be my exact number. That would be how you calculated that. Now we don't need an exact number. We're going to try to use rounding to find a reasonable estimate. So 0.41 would round to what? 0.4, right? And 220,948,915. If I wanted to say round to the nearest 10 million, that 0 would keep that 2 a 2. And that math's easier. And so what I do is this decimal place is actually going to knock off one of those zeros. And then I'm going to do 4 times 22. And I have 1, 2, 3, 4, 5, 6 zeros left. But 4 times 22 is not 44. Sorry. It's 88. Bar graphs use vertical or horizontal bars. They can go sideways. The length of the bar tells you how much it is, and then we can use them to make predictions. Let's look at this one about a man's life expectancy. So the darker blue is the men and the greenish color is the women. And we started in 1960, and in 1960, a man's life expectancy, it's hard to see here, but it was 66.6 years. And then we go up to 2005, and it went up to 75.2. So this is the average life expectancy in the United States by year of birth. So if you were born in 2005, your average life expectancy is 75.2 if you're a man.
What is it for 1995?
I don't know, but 1990 was 78.8. Oh, no, that's women. Sorry, 71.8. Okay.
What'd you say?
For a man and born in 1990, it was 71.8.
So we pretty much live like 5 years past them.
Women do tend to have a longer life expectancy, yeah. So, okay, to find and estimate a man's average life expectancy, and we're going to round it to the nearest hundredth of a year, we're going to take, guys, to find an average, we're going to take the oldest, or the most current minus the oldest, and then we're going to take the newest year minus the oldest year. And that's going to give me 8.6 over 45. So a man's life expectancy increases by approximately 0.19 years per year.
Not much.
Not a lot, no. But if you look 1960 to 2005, there was a 9-year increase in life expectancy. So now we can estimate the life expectancy of a man born in 2020 this way. So we're going to say, okay, we're going to use that 1.9 or 0.19. And we start with the oldest date, 1960. And we're going to say, oops, I'm writing this backwards. We're going to say, how many years is it between 2020 and 1960? 60 years. 40 years till 2000, and then 20 more years after that. Okay, so I'm going to take that 60, and I'm going to multiply it by 0.19. And so for men born in 2020,
Wait, did you say 40 and then 40 more?
40 and then 20. It'll be an 11.4 year increase. So I'm going to take that 66.6 and I'm going to add 11.4 to it, and I'm going to estimate that they should be about 78 years old.
When they die, they grow over.
That's the average life expectancy, yeah. So when you're talking about average life expectancy, you're averaging in everybody that died as a young child and an infant, all the way through everybody that lives to be like 100 and plus. And then they take all those numbers and they make an average. So it's, okay, so a woman's average life expectancy in 1960 was 73.1. And in 2005 was 80.4. Yep. So if I do this, I'm going to get 7.3 divided by 45, and it's actually 0.16. Now, we tend to live longer as women than men, but our gains in life expectancy are not as high. Yeah, give it a couple hundred years. So if I take somebody in 2050 that's female, how many years? That's 90 years from now, or from then?
Yep.
And then I take that 90 and I multiply it by 0.16. That's going to give me 14 years of increase. And I take that 73.1 and I add 14.4 to it, and I'm going to get 87.5. So 87.5 is your average life expectancy for a woman in 2050 if this trend continues. Line graphs. Line graphs illustrate trends over time. So women's average age at first marriage, back in the 1800s, it was 22, and then it went down to like 20, and now it's much older.
Yep.
Okay. So we can use this to find the estimate of the percentage of seniors who used marijuana in 1990. You go up to 1990, and then you go across, and we're here between 10 and 20%. Would you say we're about halfway, a little less than halfway? Where would you say this fell between 10 and 20?
15, like,
I got a 15 and a what?
13.
And a 13. Let's split the difference and go with 14. And we'd say about 14% of high school seniors used marijuana in 1990. Okay. We can look at this and say, what in which 5-year period did it decrease at the greatest rate? Well, you look at the slope, like the steepness of the line. Yeah, 85 to 90 is the steepest part of the line, right? So that would be the 5-year period where it decreased the most rapidly. Line graphs are pretty good. Okay, we're going to stop there.